Hello friends, welcome to chapter 3 of Applied Deep Learning. I hope you enjoyed the previous two chapters. They took about 2 hours to discuss the previous two chapters, and my estimation is the same for this chapter too. And as I told you, the slides are for Professor Ali Berihi at the Department of ECE at University of Toronto. Okay, we go with section 1 of this chapter. Now, we can handle architectures. We saw FNN, fully connected version 1 especially, and we talked about optimizers a little, and we talked about hyperparameters, but we want to get more deeper. We want to get a little bit deeper about optimizers, about hyperparameter tuning, and data pre-processing, which is related to data science more, but we need it here, so we will discuss it. And some tricks about training. Okay. We know that the training is this term, mean of the risk with respect to W, and W includes always and biases. And I guess this is the formula of gradient descent. As you see here, this is we have a learning rate eta specified by color red, and while in line 3 we have a while loop. This is the sub-criterion that we have, and we opted based on this formula gradient descent, and we opted the deviation, which is the sub-criterion. Okay. We always use mini batch SGD, so we call it we don't want to call it very long mini batch stochastic gradient descent, and we call it simply SGD. By SGD we mean mini batch SGD. Okay, so if we set the learning rate too small, or in better words small enough, we can go into local minima, and the speed up and optimization is evaluated by the convergence rate. And what is convergence rate? We can understand it after we understand the optimality gap. And optimality gap is nothing more than the gap between W in time t and the local minimizer W star, which is the apps of R of WT minus R of W star. It is optimality gap iteration T that we have. Okay. So the optimizer shrinks this gap as we go in the optimization process, and we can approximately say that, and please note that this is an approximation, that's approximation gap in time t plus 1 is less or equal to approximation gap in time t, and blah blah, and this drop can happen and occur in with different speeds in terms of t, and also note that it's an approximation. This gap may increase in one iteration only. That's okay. We don't want to break everything because of only one iteration. Okay, the most ideal scenario, as I can understand, is that this gap that we called it optimality gap, in each iteration it drops by a constant. For example, we call it alpha, and we want for each iteration that this drops by the term alpha. So for example, when we are comparing the optimality gap in time t, as you can see here, and the optimality gap in time 0, we then if in each iteration it drops by a constant alpha, then after t iteration it drops by the constant alpha to power t. So we can say that optimality gap in time 0 in t equal to 0 is equal to c. So we can say that if we assume or if you say that the optimality gap in time 0 is equal to c, we can say that the optimality gap in time t is equal to c times alpha to power t. So we can say that it is in order of alpha to power t, and I think you are familiar what does this order mean. You probably have taken the course algorithms and structures, and in that place it was discussed. Okay. So we talked about this ideal scenario, and if we wish to end up somewhere in epsilon neighborhood of W star, then we need that this upper bound, which is c times alpha to the power of t, will be less or equal to epsilon. So if we want this to happen, we need to have this inequality. Let me see what is it saying. If we want this to happen, if we get the log of both sides, we would have the log of, here we have epsilon over t, then we have log of a t times it would be log of c plus t times log of alpha will be equal or less to let me see what's happening here. Okay, if you get logarithm of both sides, you would have log of c plus t log of alpha will be less or equal to log of epsilon, and logarithm is an increasing function, so it would not change the side of this inequality. And if we move them for if we move log of c to the other side, and then yes, and then multiply everything by -1, we would have this equation. Okay, and for this required time, which is O of log 1 over epsilon, we say that the optimizer converges linearly, and we know that the number of iterations is proportional to logarithm of 1 over epsilon, and yes. Okay, so we know that it's a fast rate, and yes, number of iterations is proportional to logarithm of 1 over epsilon. Okay. We should note that if the empirical risk or R hat is strongly convex and we have full wedge training, We can say that yes, gradient descent always converge at this rate, but in real problems, in realistic neural networks and stochastic gradient descent, it's not that much easy to characterize this exact convergence. Yes, and so the optimality gap, which is r hat of wt minus r hat of w star, would be less or equal to L over T times eta. Eta was the learning rate, yes. So, okay, we have this conclusion. As you can see, when L gets larger, when W gets larger, L gets larger too, and so the order of this can be written as O of 1 over T. Okay. So the convergence rate of optimizers, we need this, or if we want to end up in epsilon neighborhood of W star, we need T equals to O of 1 over epsilon, and it is somehow long, you know, because the optimizer converge sublinearly, and if we just set epsilon to 10 to power minus 3 with linear convergence, we need time in order of 3, and with linear, by linear I mean the log of 1 over 1 to power minus 3, it would be the log of 10 to power 3, and it would be 3, but because we are sublinear in real world problems, we need in order of 1000. It is somehow large. Okay, sorry for the for this gap in the course. Okay, and as you may understood, we cannot use that vanilla gradient descent that we discussed before, and we have to use the improved versions of gradient descent. For example, momentum, R-probe, RMS probe, ADAM, and also learning rate scheduling. Uh, and you may ask, if we are not using the original gradient descent or vanilla gradient descent, why did we discuss it? Why did we discuss backpropagation? Why did we discuss gradient based algorithms? But you should note that all of other algorithms need backpropagation, need gradient descent, and that they are more powerful algorithms. They have the vanilla gradient descent inside them. Not also this, not only this, but also they have more than this. So don't worry about the things that we discussed up to now. Okay, if we want to have stochastic gradient descent with learning rate scheduling, it means that we vary learning rate over time. It means that we schedule it. For example, at start, the eta 0 is equal to eta, and we reduce it with t. And we can have lots of approaches that you can see. 3 approaches of learning rate scheduling here. Okay. And you can see that we can use a fixed learning rate until the test rate saturates, and we then reduce the learning rate as eta can be updated as alpha times eta for alpha smaller than 1, because it should reduce it, and repeat the above steps until test risk arrives at a desired level. Okay. For example, a good choice can be something like 0.1. Yes. Okay. Okay, and we can lead to better local minima with it. And please note that it's not changing the convergence rate, yes, because we are only changing the we are scheduling the learning rate, not changing the convergence rate, because it's something related to the plot and the nature of the problem. Okay, and you can see how do we use it in PyTorch. We can use it by torch.optim.lr scheduler. Okay, the second idea is about momentum. It is moving average. You can guess something from its name, which is average of moving, because when we are optimizing, we are moving, and here it wants to average our movements. Okay. When you want to update the weights and biases, we can simply say parameters. When you want to update the parameters, replace the gradient with its moving average. And for example, if you're in iteration t and the computed gradient is g in g of t, the estimator in gradient descent that we had before, we used w prime or wt plus 1 equal to wt minus the learning rate times g of t, but we don't want to use g of t. We want to use the moving average because maybe it's more stable. Okay, we can compute this moving average. As you can see, it is somehow averaging. It is the momentum in previous time times beta plus 1 minus beta times the computed gradient, and it with less fluctuates, it's more stable, because almost always averaging makes everything not fluctuating less and more stable, like here. And so it's an estimator of true gradient with less variance. Every time we are averaging, the variance decreases. We have proven and showed it before. Yes, and here is the update that it does. I think that's enough for this algorithm. Okay. Yes. And the next idea is Nesterov momentum, which is accelerated gradient computation. Nesterov adds an intermediate step. We can use the already calculated momentum to estimate future rates. Yes. You can see here we had this line in the algorithm of we had these two lines in the algorithm of momentum, but here we add this line, which is W hat, and we compute the gradient for this W hat, and we this time call it G hat of t, and we use this G hat instead of the G we had before. We are approximating next point based on the previous momentum that we have. Okay, I think everything makes sense until now. And yes, okay, and you can see the PyTorch implementation of momentum. We can when we want to use SGD, we can say torch.optim.sgd, and when we want to implement the momentum, we can only specify the beta factor, and also we can say that we want the Nesterov to be applied with our momentum or not, and if the beta is equal to 0, the m the previous m would be ignored, and so everything would be the gradient, so we won't have any in this case we won't have any momentum. So we can say SGD is a special type of momentum if we set beta to 0. And yes, the implementation is easy in PyTorch. Okay, the next algorithm that we are going to talk about is RPROP, the resilient backpropagation. And yes, and if here it tells us that if we have individual learning rate in each dimension of W, we may recall it the first you don't have access to assignments, but we had in our assignment that we had. Okay, the idea is that we have individual learning rates in each dimension, and for the one-dimensional case, you can see it's like this, but the learning rate scalar would be something like the thing that you see in this picture. And we can say we are going fast, or we are slowing down, and when the sign of gradient is not changing, we keep going faster, and when the sign changes, we are notified that we have passed the minimum, so we have to slow down and get back in that dimension. Yes, you can see the picture here. We keep increasing until we pass the minimum, and we get back, and we can apply this idea on every entry and every dimension individually, as you can see. And yes, our purpose nothing very hard or special. You can see the factors mu plus and minus, and yes. And we should not choose mu plus and mu minus in a way that their product would be 1, because we are not going to move exactly to the previous point that we were. Okay. And the next algorithm would be RMS probe, which I will discuss. Let me have a break. Okay, we now go to the next part, which is our, I think, fifth. It is the fifth optimization algorithm based on backpropagation, which is RMS probe, or root mean squared propagation. We saw R probe, which was the resilient backprobe, and R probe only works fine when we are training in a full batch setup. And why? Because it ignores the magnitude of the gradient, and yes, it only talks about the if it is it only cares about its sign, it doesn't care about its magnitude. And if you consider this example, you can see that in this slide, when we are in 1, 2, and 3 steps, it's having larger and larger learning rates, and when in last step we come back with a smaller step, and yes, we probably have lost our we probably lost our local or our optimum point, the minimum point, because we were speeding up in our 3 sections. So you can see the name of Jeffrey Hinton. He got Nobel Prize some days ago. Yes, he came up with a solution. Yes, we can have a moving average of learning rates. And we can have an average of gradient magnitude. So we can update the R probe in this way. That's when we want to update the W. We can write it in this way, and so yes, here we don't. Here we will. Let me see. Yes, here we somehow not completely ignore the magnitude of gradient, and yes, you can see here, for example, here is RMS, root mean squared rho, root mean squared, and it is V of t here, and it is getting normalized by V of t, and here we can get it updated. It is RProp inspired, but not RProp, and yes, so you can consider this algorithm as this pseudocode here. Okay. And The typical choice for beta is usually something near 1, and for example 0.9. Yes, and oh, and one of the most popular optimization algorithms that we have here though is the ADAM optimizer, which is adaptive momentum estimation. It was proposed in 2015, and it combines RMS prop with momentum, and so we have momentum for updating the weights and our prop inspired approach for normalization, which is the scheduling algorithm. So you can see the overall algorithm of momentum here, sorry, of ADAM here. Yes, and here are the usual parameters that we set, and yes, that's it. Okay, and we have saw lots of algorithms here, and we have first order minimizers which use first order derivatives, and all of the things that you have seen were first order optimizers. We have also second order minimizers, optimizers that use something like Hessian, which is a second order derivative, and in these approaches are using Newton's method, and Newton's method shows that convergence of gradient descent is improved if we multiply inverse of Hessian with gradient, and they have better convergence rate, and but in computation they are worse as expected, because always you have trade-off, and yes, even if we use approximate Hessian, we need a higher computation. Okay, everyone, we are on the second section of chapter 3. I decided to make it two parts. You know, I want to make it chapter 3 part 1 and chapter 3 part 2. So you're now watching chapter 3 section 2 part 1. Oh, it maybe it's somehow confusing, sorry. Okay, so we now want to talk about how can we tune hyperparameters, and because they are not learnable. By learning I mean gradient distance, gradient, something like that. Okay. One problem may become to mind is that shouldn't we make the neural network as deep as possible? No, because we may see the problem of overfitting. Okay, now you can see, for example, here we have a problem. We want to learn it. We assume it is a polynomial function of degree 2, and it would be, you know, more sophisticated than real world, and so we face the overfitting problem in the real world. The key hyperparameter in this network is P, and as you can see, P is the degree that we have here. Okay. you know that we have to split training the data to training and test, and we start training using gradient descent, and then we test it on the test data, and yes, the naive conclusion is that making the neural network larger is always good, but it is not. It's a beautiful plot that you can see for the hyperparameter and test race. This curve shows that up to some point increasing is good, and after that point it's not good. Yes, and as we pass p equal to 2, we are overfitting, and overfitting occurs when training fits the model, which is you know, the network cannot generalize this data anymore to new data points. Yes, and what's the generalization? It means that for example, the model, when we say it generalized good, when it can predict the test risk, test data points that it haven't seen, and it yes, and you can see the overfitting here. Okay, and underfitting is the opposite of the overfitting, and happens when the network does not have enough parameters to train. Okay, sorry for the delay here. Okay, and you have seen here what is the cause of overfitting. Okay, and okay. Okay, we can use the validation, but it takes time. So we have some better points on how we can do this tuning of hyperparameters, like regularization, dropout data augmentation, that we will discuss in this part. I think almost all of them would be in the next part of the video. Okay, and the important question is that when does overfitting happen, and it's the key question to know better about the approaches that we want to talk about mitigating overfitting. Okay, okay, so the overfitting happens when our model is very complex, and it's suited for learning complicated functions, so overfitting happens when the model has a large capacity, and yes, that's it. Okay. And you understood the model capacity definition is the ability of a model to learn different functions, and so Okay, you can see the data size, and when we have a larger data set, uh, you might think in which case, uh, when we increase the number of data points, the overfitting is reduced. Okay, so uh, the second thing is that you know, the our training data set is small. Just think about it. So we talked about the model capacity is high and the training dataset is small. So the more learnable parameters the model has, the larger the training dataset should be. It's a very important general rule that we should think about it. Please read it again for yourself because it's very important from my side of view. Okay, the more learnable parameters the model has, the larger the dataset or the training dataset should be. It's very important. Okay, and another aspect of view to see overfitting is that we should see that how the parameters in model change as we iterate over it with the optimizer. And for example, consider we have a higher capacity neural network with p equals to 5, so it is a polynomial of degree 5, and we have data set of 8 data points, and we train it using full SGD. Okay, start training it, and you can see that the final goal is to reach this point, which is the optimal and best answer to this optimization. But you can see you're getting closer in time t2, but in time t of n you're getting worse. Okay, so it seems that we should stop our training in a time, you know. So the ways to start to get close to the optimal solution in some intermediate number of iterations, but further training will start to deviate, or in other words overfit. So think about this curve. Okay, so we call it co-adaptation of the parameters, and so the initial iterations are good and beneficial, and you know, after we have we have got closer to the ground truth, it starts to overfit due to noise. You know, so W3, W4, and W5 try to co-adapt. You know, the in first iterations, neural network tries to learn the real function, and at some point it starts to learn noise, and it is the most observable implication of overfitting with neural networks. Okay, and a typical learning curve is like this, and I think you can understand it. Overfitting starts from this point, and yes. So We now know that overfitting is caused by large capacity of model, smallness of dataset, and auto-adaptation, which occurs because of the large number of training iterations. And we should note that, for example, the third one is related to the first and second one, and also they are correlated with each other. You know, there are some ways to avoid avoid overfitting, but I think it's enough for chapter 3 part 1. We can continue the rest in chapter 3 part 2. Best luck and goodbye.